So today, I talk about many things today. So hope that I'm afraid that some people might be distracted, but I talk about basically generalization of what I talked about in AdS 5 CFT 4 in various other dimensions. First of all, I'll try to give you some unifying fixtures for all even dimensional SCFTs and their indices and their Cardi limits, and trying to use them to understand some large black holes. And then I'll try to explain to you certain examples. So the even dimensional Cardi free energy will basically be rederived, or at least highly constrained, using Tooft anomalies or some discrete symmetries that we think we know about these CFTs, even for non-Lagrangian theories. And then trying to turn to odd-dimensional CFTs and their dual AdS4, AdS even black holes, using similar Cardi-like limit of the indices. And this last example will turn out to be fairly more complicated. You just have to work in a dirty manner. Okay? So let me just briefly start from this first slide. How many interesting superconformal field theories that we know in various dimensions, apart from 4. So I don't really want to go through landscape of examples. I really want to stay within the simplest model in each dimension. So let me explain to you the class of models that we should at least briefly discuss in this talk in 3, 5, 6-dimensional spacetimes. In 3 dimensions, probably the simplest kind of superconformal field theory for string theories will be those living on the world volume of multiple M2 branes. They're enjoying maximal superconformal symmetry in 3 dimensions, and they're supposed to have the Lagrangian dual on AdS 4 times S7. Okay? And very funny fact known about this system, mostly from the gravity duals, but nowadays we are getting to have more field theory intuitions about that, is that the Lagrangian number of degrees of freedom on this system is scalarly like n to the 3/2, much smaller than n squared. Okay? So if you engineer this system from a UV gauge theory, which is weakly interacting, and try to realize this as a strongly coupled fixed point, there should be a huge reduction of degrees of freedom from n squared. Okay, in 6th dimension, we also know very simple conformal field theories living on the stack of parallel M5 branes. We call it 2-0 field theory with maximal superconformal symmetry. It's also known to have Lagrangian gravity dual on AdS 7 times S4. A much more mysterious fact than the M2 brane degrees of freedom is that in the Lagrangian dual, various indirect studies, for instance from gravity, show that the number of Lagrangian degrees of freedom should scale like n cubed. It's much larger than, let's say, n squared living on D branes and so on. So these 2 examples, at least if we, for string theories, most string theories, it's very, very well known because there are 2 basic objects in M theory. Perhaps less familiar objects might be 5-dimensional superconformal field theory, but it has been also found in very early days of the string duality by Seiberg. Okay? The simplest kind of theory that I'll briefly mention at the last stage of my talk are the 5-dimensional CFT that Seiberg engineered, basically, living on stacks of D4 parallel D4 branes. If you just have D4 branes, they are never related to strongly interacting CFTs. Seiberg engineered this D4 brane quantum field theory to be probing the background of D8 brane and orientifold A planes. So if you have these 8 brane backgrounds, they source the linear inverse dilaton field in type 2A string theory. So whenever in a transverse direction is an 8 brane located, it provides a cusp of this inverse dilaton. It changed the slopes. Okay? So if you locate the D4 brane at a particular background, the dilaton value is the inverse of the gauge coupling on 5-dimensional gauge theories. But the Seiberg's idea is to tune this background parameter so that these 4 brane systems are located at the tip where the coupling constant is supposed to be diverging. Okay? So by taking the strong coupling limit of this string theory system and decoupling gravity and so on, Seiberg gave certain abstract arguments or claim that a strongly interacting superconformal field theory should be living on this strongly interacting limit of this D4 brane system. For instance, in this kind of model, it's a complicated SPN type gauge theory. It's coupled to certain matters and so on. But you won't have to remember all too much details in this talk. This system is
running inverse dilaton was just a concept. Roughly, you can think of that solution as just the 08 solution.
Yes. 08 is creating this cusp here. So if you had just D8 branes, it will never give any strongly interacting point like this. So even if you don't have any D8, just O8 makes this slope, and it gives you a strongly coupled field theory. This is also known to have Lagrange gravity dual, and AdS6 times S4 with this orientifold action having to do with the O8 planes. Okay? So these are three quantum field theories that I'll have something to say about in this talk.
And this is some theory which in the, if you sort of go off on some Coulomb branch or something, becomes 5D Yang-Mills theory?
Yes, yes. So the thing is that the relation of these strongly interacting theories and the Yang-Mills type gauge theories are very subtle. So for the first 3D CFT, it's often related to the weakly interacting Yang-Mills or Yang-Mills Chern-Simons type gauge theories in the UV, realizing the CFT in the IR. The other two are related to Yang-Mills theories in a much more subtler way. We don't know any microscopic descriptions of that. So for instance, if you deform this CFT by certain relevant deformation, massive parameters, and then in the weakly coupled limit, there is an effective description of Yang-Mills theory, where this massive deformation parameter is the inverse Yang-Mills coupling. This is also related to Yang-Mills theory in a subtler manner. If you compactify this system on a finite circle radius, this circle radius at low energy turns out to be the inverse gauge coupling of the maximal super Yang-Mills gauge theory. So, yeah.
And in the 5D case, that deformation is like going to the right of the class.
Yes, yes, going to these bold ones. Yeah. And so in these two examples, we really don't have any microscopic definitions or formulation of the theory, but still, it will be very interesting to see how this. By the way, this AdS6 is supposed to have this strange larger number of degrees of freedom, much larger than n. So in these both cases, at least from the gauge theory effective description that we know, it will be helpful to have a better intuition on how these enhanced degrees of freedom will be happening. And that will be defining indirectly the novel deconfinement which is supposed to exist. Because in the AdS dual, Hawking-Page transition of black holes are just appearing as it used to appear in AdS5. But if you get to the field theory dual, the meaning of deconfinement probably should be much more complicated, and probably it will, understanding it a little better, will be giving hopefully a hint on what this quantum field theory should really be. So that's one main reason why I wanted to do similar exercises of free energy, larger and Cardiff free energies in these examples.
So AdS6 times S4, that's type what?
Type 2A. Type 2A.
And is the coupling constant a free parameter?
Oh, no. Well, yes. Yeah. There is a parameter. To get this kind of solution, you need CFT. So you take this parameter to be 0, inverse coupling to be 0. So there's no free tunable parameter left, but still the dilaton is running in this background in a very complicated way. So it's a very complicated warp product. It doesn't even have It doesn't even have SO5 symmetry. It's complicated.
But the dilaton is constant on AdS6.
It's constant on AdS6, and it appears on the warp vector depending on a coordinate of S4. You know, S4 is here. You cut it in the equator, this what do you call it, latitude coordinate. Dilaton depends on that because it's a distance away from the orientifold plane.
And so because it's a function, there's no real parameter in that. Is there a constant? I was just wondering whether there was some weakly coupled limit. Weakly coupled string limit of this, of the dual description.
I think if you go,
but not in the conformal point. The conformal point is never weak.
Never. Yeah, right. Good. Yeah. Yeah.
Is this the fact that the number of degrees of freedom is n to the power d by 2?
And
is the universal fact about CFT?
In these examples, is
6 by 2. Does it work? 0 to theory.
6 by 2.
Oh yeah, that's 3.
Yeah, 6 by 2.
Yeah, that's interesting.
That's interesting, but I'm a bit cautious to say this because in these two examples, it's definitely true, and I think these are generic phenomena if you stick to M2 branes and M5 branes.
But if I think about abstract CFT, large
there are counterexamples. For instance, if you consider this D2 brane, large D2 brane theory, the large number of D2 brane CFT is a massive 2A theory. It scales like n to the 5 over 3 or something.
in CFT?
Yes. So you put stack of D2 branes, not in massless 2A, but massive 2A. It has different larger scaling. Also in 5-dimensional CFT, recently this Gott-Pearl and Ulleman and company has engineered this many large and gravity AdS6 duals. based on this intersecting fibrine webs. And in that case, the Lagrange scaling is quite different from this. This is very special to this orientifold example Cyborg has mentioned. So for instance, if there are large n numbers of NS5 and D5 branes, the generic behavior is that they scale like n to the 4th power. So it's a bit, but yeah, in this example, they are coincident. Yeah. Anyway. So I'll try to say something more universal in even dimensional quantum field theory first. So first recall that for 4-dimensional maximal super-Young-Mill, in the first lecture, I provided a derivation that the Cardi free energy, when the angular momentum chemical potential are small, should be taking this rational function form. And in the numerator, I just got this result by deriving it from free theory's matrix integral for the index. But it's a cubic polynomial of these R-charged chemical potentials. And one can easily notice that this is the anomaly polynomials of the 't Hooft anomalies if you restrict yourself to U1 cubed part of the SO6 R symmetry sector. Okay? Probably this structure will generalize to n equal 1 CFTs and so on. So the question is whether one can make a derivation of this more abstractly or intrinsically, just using 't Hooft anomalies only, okay? And using some, yeah. So the answer is almost yes. The 't Hooft anomaly basically determines this term in certain approach that I'll present to you. It almost doesn't rely on, it basically doesn't rely on the existence of Lagrangian either. The answer is almost yes. The 't Hooft anomaly determines this term, but there are certain possible extra terms that has to be forbidden to really derive this, and that is justified in the maximal super-Young-Mills case by certain discrete symmetries, some generalized notions of parities, or the Weil symmetries of SO6, and so on. So almost, yes, anomaly will determine it. But this kind of method suddenly can be applied to more general class of more challenging quantum field theories, mostly to non-Lagrangian quantum field theories in even dimensions. So, yeah.
This is only in the Cardi limit? Yeah. It's like the zero-size circle limit.
Yes.
Like a 3D partition function.
Yes, basically, yes. So I'll be using basically a 3-dimensional technique of background fields to derive or argue that this should be the case, inputting the knowledge of 't Hooft anomalies and certain symmetries. So I'll try to apply, first rederive or argue for this for maximal super-Young-Mills and apply the same technique to 62-0 CFTs, living on multiple M5 branes. It will turn out that knowing the anomaly almost derives a Cardi free energy, which accounts for the thermodynamic properties of large supersymmetric black holes in AdS 7 times S4, but with some certain assumption which I think is mild, and which I think can be proven in the near future, but you'll see. Okay?
So this sort of reminds me a little bit about some papers by Kumar-Gotsky and some company about 3-4 years ago,
yes,
where they tried to talk about the high temperature limit.
Yes, I'm just going to generalize this with a phase included as well. You know, in the first lecture, in a sense, I just repeated their calculus. You know, Kumar-Gotsky and Di Pietro had this Cardi formula, A minus C. Yeah. They also had 2 arguments. They just basically did the calculation when the theory had a weakly coupled limit. It's basically the first lecture of mine. Secondly, they argued for it using abstract background fields methods and 3-sphere. Today, what I'm going to do is exactly that with phase factor included. And the story will be much more subtler, but it will turn out to work. Yeah. Good. So let me try to explain the basic setting. I want to consider, I want to first realize the chemical potentials appearing in this index as some background fields on S3 times S1, and it's quite easy. Chemical potential, so I'm going to consider this index, and when this condition for the index is met, I mean constraining the chemical potential, without this first factor that I included, it just becomes an index. For the purpose of making a Kaluza-Klein reduction on small circles somewhat easier, I introduced this regulator, e to the minus beta, coupling to the energy or scale dimension. So if you impose this condition and take beta to be 0, okay, it will be an index. Okay? I will do the calculation with small beta and other chemical potential satisfying relation, and I'll study the high temperature limit of the index by setting this angular momentum chemical potential to be small but fixed, and I'll take this regulator parameter to be 0. If you'd like, you can slightly modify the definition by allowing beta to couple to energy minus BPS energy, so that it really couples to Q daggers anti-commutator. And then you can believe the fact that beta dependence should just go away, and you can feel more free to take the beta 0 limit. But anyway, this slight different definition on what beta couples to is just modifying the definition of deltas and omega by a small shift by beta. So basically, even if you work on this setting, you'll be able to study the index. Anyway, the background gauge field responsible for the internal symmetries chemical potential is given as follows. They're just holonomies on the temporal circle, compactified in a period, basically circumference beta. Okay? The chemical potential for the angular momentum is encoded in the twisting of the coordinates on S3 times S1 in the following manner. So had this been epsilon, it's just a round 3 sphere times S1, where this N1 and N2. I'm using the standard coordinates of theta, phi 1, and phi 2 for 3 sphere, and it's slightly twisted product. Okay? And what I'd like to do is to study the free energy of the index in the formal high temperature limit, meaning small temporal circle in certain sense, in the limit in which beta is said to be 0, and also omega is said to be very small in this limit. Okay? And to see if these kind of things are doable, we rearrange this metric, expand this complete square, and recompact and remake the complete square into delta tau, d tau plus something square in the following manner, so that it's the suitable metric for Kaluza-Klein reduction of the small circle. If you rearrange it, and these dirty pieces are coming out, and these are kind of squashing in a particular manner the resulting 3-sphere metric in the base. And the off-diagonal term here is canonically called the graviphoton field. Okay? And the coefficient appearing here is basically called the dilaton field. So this one multiplied by beta square is giving you the circumference of the tau circle. Now you see that the structure is very complicated. The effective radius of the circle is depending on the base size. So if you multiply beta square, it becomes the radius square. It has a term proportional to beta square. It has a term proportional to omega square. So it's very complicated. But anyway, you should take omega and beta both to be small, to have something like small circle. Okay? And what I'd like to do is to consider, in the high temperature limit, the effective action of the background fields in this 3-dimensional language. And these non-trivial effective action will be generated in principle by integrating out the dynamical 4-dimensional fields in the Kaluza-Klein sector of this circle. Okay? So if you integrate out these all Kaluza-Klein towers of 4-dimensional Yang-Mills theory, it will give some effective action for the background fields. Okay? So that will be non-trivial contribution to the effective action. There will also be a contribution for the reduced remaining 0 modes of the dynamic fields on the 3-sphere. One can sort of easily argue that that kind of term should be subleading in this Cardi-like limit. Okay? So this is the basic setting of my study, trying to understand the structure of the background effective action of these 3-dimensional background fields in this Cardi limit. And the background effective action will be formally be arranged into an infinite tau of derivative expansion, which we'd like to study from now.
So you don't need the betas to be smaller than the deltas?
What is? Sorry?
Oh,
beta smaller than delta. You mean that?
The beta is smaller than the omegas?
Yeah. Delta is kept order 1. So its real part is again small and fixed, because it corresponds to large charge, but it will turn out to have order 1 imaginary part. So delta is just kept order 1 complex number. And this I take to be small because it's basically a regulator which I like to eliminate. So this is smaller than whatever physical parameters. Yeah. You know, had this beta been coupling to not to the energy but BPS, which is Q dagger from theta, you generally expect that the beta dependencies appearing here and there in the effective action will completely cancel if you impose this index condition. Of course, I have no power to supersymmetrize all the background field effective action, so I just believe that beta 0 limit is smooth and just consider the leading terms. Okay, good. So if you know Komagorski's 2014 work, it's sort of generalizing it obviously, but in a more dangerous way because I turn on much more complicated background fields. Okay, so Cardi limit, there are many. You might think that this derivative expansion business will be complicated. I've explained to you a few terms that can be written down. It's the gate.
Sorry, let me just check.
Yeah.
It's the size of the sphere is much larger than the size of the Thorne circle.
Oh yeah, yes,
That
yeah,
is what is governing.
yeah.
That is what is giving you power.
Yeah. So I basically made things dimensionless, and when I say this, it's all divided by the radius of the 3 sphere.
Right.
Yeah.
And so basically, you could do this on any background.
Yes.
And you happen to be working on this kind of sphere.
Yes. Any background means what?
Any basis background.
Oh yeah. Of course you can do that. Yes. Yeah, definitely. Yeah. There are more generalization than this work, which appeared recently in Masazumi Honda's work on other 3-dimensional backgrounds. So it should be quite obvious, I think.
And how much are you using supersymmetry here? Are you using the fact that this theory preserves, this integral preserves supersymmetry?
No, I almost don't use supersymmetry. So what I'm using is that this limit is well defined. If you don't know supersymmetry, if there's no structure like supersymmetry, this is formally the high temperature limit rather than eliminating a regulator. So this limit will be highly singular in general grounds. Okay, but if you keep basically keeping these parameters larger than this inverse temperature like parameters will be illegal if it's not the index. But if you study the context of the index and allow beta to be coupled to, let's say, this quantity, beta taken to be 0 with other parameters kept fixed is believed to be safe. Okay?
I'm sorry to slow
Yeah.
you down, but
Yeah, sure.
why is, so suppose I keep omega to be order 1 and take beta in a non-supersymmetric situation. I have a very small thermal circle and I keep the phase of omega to be order 1.
Phase of omega to be order 1. The smallness of the thermal circle is played. It's guaranteed by a smallness of both. Beta square times this dilaton parameter is the effective radius square. So it's beta square term, there's omega square term. So you have to take Hardy limit as well. In BPS sector, it's easier to explain because the angular momentum contributes to BPS energy. In general case, I don't know how to argue it more simply.
Suppose omega was half, for instance.
Just half, order 1.
Yeah. So I mean, I pi.
Just
a -1 phase for things that carry some angular momentum. That's the kind of thing we do with fermions rather than bosons.
Yes.
But it's okay to take high temperature limits of both fermions and bosons.
Yeah.
It's not totally clear to me that you couldn't. Okay, that there is a problem. I mean, for instance, in our hydrodynamic stuff, if we turn down. Okay, I'll ask you later.
Okay. Yeah. It certainly confuses me, but anyway, this is the setting that I'm working on. But anyway, if you try to study the structures of these, where are I? So these are some examples of background fields. And formally, if you go to higher derivative sector, there appears to be more factors of dilatons. So
wait, I'm sorry to interrupt, but are you going to use this to basically rule out terms that grow like t to the power d minus 1?
T to the t.
Your beta to the 1 over beta to the power d minus 1.
I'm going to rule out almost all tau terms in positive powers of beta. I'm going to take beta to be small. And almost all terms, except finite number of terms, will be carrying positive powers on beta.
Yeah. Now in hydrodynamics, what you would have got is t to the power d minus 1.
T to the power d is what? Dimension.
D-dimensional field theory.
The leading term.
Yeah, you would have got a t to the power d minus 1.
Yeah,
because that's just the log z.
Yeah.
Log z goes
Yeah.
And what you're saying is that term is absent. I think that's what
I'm going to show you. Actually, that term is hidden in here. I'll illustrate the difference. Okay. But anyway, let me try to emphasize the certainty of this approach, because naively, if you make derivative expansion, terms with more and more derivatives addressed with more dilaton factors, which are formally suppressed, that you might expect that you should expect derivative expansion should be good, and you can just consider the first few terms. But notice that various 3-dimensional background field itself has singular behavior in beta. So chemical potentials are naturally some finite number divided by beta. So the field itself are singular. So the usage of this derivative expansion might be very subtle than you might naively think. Okay? So, had this effective action, if you wanted to use this effective action for general purpose, effective action for background field is good for many purposes. If you take functional derivative of effective action in background fields, you can get some correlation functions of fields, perhaps depending on these background fields and so on. If you're going to do that, making functional derivatives, I'm pretty sure that the formal derivative expansion arrangement will be ruined by these singular background fields. However, my purpose is much, much more modest, and I'm going to just use restrict the use of this formal derivative expansions, I mean, effective action arranged in this formal derivative action, just to study the equilibrium partition function. Okay? More specifically, I'm just going to plug in the values of these singular looking fields into these kinds of infinite towers of terms with suppression factors given by dilaton, and just do the integral, see whether they're suppressed or not, as a free energy of the effective free energy of the partition function of my index. It turns out that just plugging in these singular fields and integrating over the 3-sphere, infinite tower of terms are indeed suppressed, and these suppression parameters are being small betas or these angular momentum parameters. So at least for this purpose, I regard this derivative expansion as a high temperature expansion of my free energy, and that seems to be working well. Okay? Yes, so I'm going to make a restricted use of this effective action, although the background seems to be taking some dangerous values.
Can the beta cube terms go away?
Beta cube terms, one of beta cube, I'm going to explain to you. So these are some effective action terms. So the leading term is the derivative action in the naive sense will be the cosmological constant term. So cosmological constant term is by dimensional grounds dressed by 1 over radius cube. Okay? So if you evaluate it for general background of my sort, you get this expression. So beta, if it had been a non-supersymmetric setting, would be the inverse temperature. This is the rotation parameter. Okay? So in physical setting, in which beta is a real inverse temperature, you cannot take beta much smaller than omega. So in this case, you'll get the beta fourth, beta first, so t to the cube factor. Okay? In my setting, I do the index. I keep the omega fixed and take the regulator parameter to be small. And this will, if I take this limit for the index, this will turn out to be suppressed rather than amplified being t to the cube. So the naive derivative expansion is slightly rearranged, but still the infinite towers are getting suppressed. This is a very subtle thing. So the naively dominant term turns out to be suppressed. The next term is this Einstein-Hilbert term, and its partner term, what's this? This graviphoton kinetic terms and background fields kinetic terms. They all turn out to be suppressed in positive powers of beta. You can go on, and it just gets more and more suppressed. I think one can make a proof, but I'm practical-minded, so I just asked my collaborator Juno Kim to evaluate tons of terms on Mathematica. I think he did almost 100 terms and so on, and organized up to some order, and it really gets suppressed. So I think it's a proof of the fact that almost all terms in the derivative expansion get suppressed either in small beta, and only the leading term, which are in the 0th order in beta, and also in the leading order in small Cardi limit, comes from the Chern-Simons terms. Notice that in the usual thermal partition function without index, the cosmological constant term that Shiraz mentioned is the dominant term, and the Chern-Simons term is the next leading order, if you want to study some charge effect and so on. Here in the index, this order is reversed. This is suppressed, and Chern-Simons term will be dominant, somewhat curiously, if you take the scaling limit for my index. So I only have to investigate a finite number of Chern-Simons terms and try to evaluate them, constraining their Chern-Simons levels. Okay? If I do that, I'll get the leading Cardi free energy. So all the beta to the 0th power term are classified into the following things. So you might see apparent beta dependence, but if you plug in the background and do the integral, they all turn out to be beta to the 0th power. It turns out that there are 2 classes of Chern-Simons terms of background fields on 3-sphere, all coming with quantized coefficient. The first class turns out to be usual gauge invariant Chern-Simons terms for graviphotons for the Cartans of SO6 gauge field. So the I runs from 1 to 3, and the mixed Chern-Simons term. Okay? But from n equal 4 super-Young Mills, just by using some discrete symmetry arguments, you can rule out all these terms completely. There's some subtleties in doing this argument, but just by using symmetry, you can easily rule it out. For instance, this is very easy to rule out. Just from the Weil symmetry of SO6 is just ruled out. And the other things can be ruled out by using some parities and combining with Weil symmetries and so on. So if these coefficients were non-zero, it will contribute to the leading order in the Cardi free energy, but their coefficients are zero, forbidden by. So if you integrate out these Kaluza-Klein modes of manifold for Young-Mills, coefficient will, this Chern-Simons term will not be generated.
So could I
yes.
just, I'm trying to understand your general setup.
Yeah,
Should I say it this way? That naively what you're doing in this partition function is looking at the action for the zero modes. Not in your setup, more generally, you look for the action for the zero modes by integrating out the Kaluza-Klein modes.
Yeah, yeah.
And
zero mode means dynamical fields.
Or just Euclidean in a Euclidean way, those that don't depend on the circle.
Okay. Yeah.
Because the circle is so small, those are much lighter than all the Kaluza-Klein modes.
Yeah.
Then you integrate out the Kaluza-Klein mode, you get some effective action for these for these things.
Yeah.
And that's a reasonable setup.
Yeah.
Now what you've done is twisted that circle.
Yeah.
With a twist of order 1.
Yeah.
Which means that there are no zero modes.
Because
any field that, well, at least that is charged under your twisting, would pick, even if it had no momentum. Yeah, the minimum momentum is now quantized in units of that is twist plus integer.
You can alternatively say that these formal zero mode fields are coupling to the three-dimensional background fields.
You can say it that way, but roughly,
yes, it's sort of giving masses or something.
Yeah. You've turned down an omega.
Yeah.
Right, so suppose omega was a phase,
yeah.
Some fractional multiple of 2 pi, then anything that carried angular momentum would be quantized now in 0, 1, 2, 3.
Yeah.
But that phrase alpha, 1 plus alpha, 2 plus alpha.
Yeah.
And so its energy would be alpha by r.
Yeah.
The lowest energy,
yeah.
And as long as alpha was fixed, this would also be massive.
But the thing is that this parameter, the parameter which gives large mass, or the large mass to what I call zero mode, will be given by the small circle radius. And the small circle radius's role is played not just by beta, but just also by small omegas. So if you really want to capture the diverging Cardi behavior, which depends on omega, in principle, you might worry that this zero mode fields coupling to this omega might give some effect. But anyway, what I give is that what I call this zero mode effect can be analyzed, and in the free energy, they are only argued to be proportional to log of omega. So it has some omega dependence, but it's sub-leading than my Cardi limit. Okay?
But charged fields, for instance, have no zero modes. You've turned on for your charged chemical potentials. You've turned down phase chemical potentials of order 1, right? So.
Yeah. So four-dimensional Yang-Mills theory has 6 scalars, and they all rotate in deltas. They don't contribute to this divergence. Probably, as you say, you can ignore this. This is coming from the one real scalar coming from the holonomies.
Very good. This is because this is the only zero.
Yes.
Okay,
Yes. So if you reduce it to 3 dimension, it has 7 scalars, and the last comes from the holonomies.
Yeah.
And these holonomies, non-compactness is only cured if you. It has some infrared divergence in the 3-sphere partition function. It's cured by finite but large 1 over omega.
So you're not turning on a large imaginary chemical potential for omega.
No, it's just taken to be small as a complex number, as I did in the previous.
Wonderful. So things that have large angular momentum are still massless, but things that have large SO6 charge are very massive and won't contribute. Okay.
Good. Thank you. Okay, so only to investigate Chern-Simons terms. And these terms are gauge invariant Chern-Simons term. One can argue it's all forbidden. But there's one more curious gauge non-invariant Chern-Simons term, which to the best of my understanding has been worked out by Shiraz and company, I think in the course of studying hydrodynamics and so on. So the idea is that you study the partition function of S3 times S1. It's a 4-dimensional field theory partition function which has Tooth anomalies. And due to Tooth anomaly matching, even the high temperature limit of the partition function should respect this Tooth anomaly. So if you vary the effective action with this gauge transformation for background fields, it should be non-invariant. And the way you account for that in the high temperature limit effective action of the 3-sphere is to have certain Chern-Simons terms which are not invariant under this gauge transformation. So it's not really the canonical Chern-Simons term. It has the 4th component of the gauge field along the circle appearing here and there. So it's not gauge invariant. But this kind of term structure is determined so that its variation is sort of giving the right non-invariance of the effective action dictated by Tooth anomaly. So understand that basically the truth anomaly is dictating all the combination of these fields, and furthermore it determines this coefficient this way.
When you say gauge invariant, it's the gauge transformations of the
Background fields, yes. So it's really a global symmetry, SO6 R symmetry, yes. So thisCijk appearing here is exactly the coefficients of the cubic anomaly polynomial of this SO6 anomalies, I mean the U1 cube part. So this term is forced to exist, and this contributes to the leading order in the Cardiff free energy. So you just have to plug in our background fields, evaluate it. Okay? You just do that, you get this expression. If you
fix the coefficient of this
here? Here? I mean, from anomaly. Its gauge variation is required to be a specific expression. Basically, the three-dimensional reduction of the four-dimensional, what is it, f wedge f times n squared or something. Yeah. So plug in and evaluate this. You get precisely the same expression that I explained to you by doing some detailed calculation using this unitary matrix integral. So it's much more abstract derivation, I think. Of course, this derivation also has certain caveats, like whether the maximally deconfining saddle points are the most dominant one. I explained to you those issues in the first lecture. Even here, there is corresponding subtleties. So I tried not to show these subtleties at all, but there are comparable subtleties similar to what I explained in the first lecture. But anyway, assuming that, you can derive this. Now the interesting part is that you can try to apply this technique to more general quantum field theories. So six-dimensional 2-0 theory. So I won't even explain to you what the index is. It's a suitable partition function of radially quantized conformal field theory, an index. So you can regard it as a supersymmetric partition function on certain twisted S5 times S1. You take the really similar type of small circle limit, taking now you have three angular momentum chemical potentials, omega 1 to 3, and the formal regulator parameter beta. You take it to be small. You find that all other terms are suppressed, except the Chern-Simons terms. First of all, the gauge non-invariant Chern-Simons terms can be also determined from anomaly matching and anomaly matching argument. If you keep the U1 square part of the SO5 R symmetry, its anomaly polynomial is proportional to n cubed in the larger limit. So you get this kind of complicated Chern-Simons term. Yeah. Plugging in the background and evaluating it, you get this number. This will turn out to be the free energy explaining large supersymmetric AdS7 black holes. Yeah.
Earlier, one of the first few slides, you had said that this is, you can show that this is coming from the anomaly, but you also need some input from having some discrete symmetry.
Yes, so for n equal 4 Yang-Mills, that was used to forbid the gauge invariant Chern-Simons terms. You know, if n equal 4 Yang-Mills theory has certain parity if you make a similar action on the SO6 chirality. And for instance, graviphoton Chern-Simons term is blind to SO6, so just parity forbids this term. And this is forbidden by the Weil symmetry. Weil symmetry, because it's, SO6 Weil symmetry is flipping the sign of two Cartans. So if you choose this to be one of the Cartans, it just goes away. And combining these two symmetries, you can also forbid this, no matter whether it's a mixed Chern-Simons term or direct Chern-Simons term.
So
but
if those were not forbidden, then this final result would be different.
Yes, and that I think is happening in the 62-0 theory. And that's the very, very loose point. So I explained to you that the gauge non-invariant Chern-Simons term dictated by anomaly gives nice result in the larger limit. Other infinitely many terms arranged in derivative expansion, we showed by evaluating many terms that they are suppressed, indeed, except the gauge invariant Chern-Simon term, which have these structures. And I find no arguments based on symmetry that they should be forbidden, and I think some of them are actually not forbidden. I mean, the reason why you can't use this argument is that, for instance, for maximal super Yang-Mills, I basically use parity to forbid this term. 2-0 theory is basically chiral. You can't forbid this, right? And I mean, some other terms you can forbid. I think you can forbid this term and this term based on Weil symmetries only. But I think this term and this term doesn't have specific reason to be forbidden, just based on symmetry. So I don't know what to do in an abstract manner. But there are some signals, I think. I think Chern-Simons coefficients can be basically determined by studying any partition function with circle factor. As Shiraz mentioned, not just S3, S5, but other partition functions of various sorts, as long as it contains a small circle. Recently, six-dimensional CFTs, supersymmetric partition function has been studied by this and that method. And there's a signal that, at least in the context of S5, There's the paper by Zohar Komagorski conjectures that this coefficient is 0. And I think conjectures that this coefficient is the first power of n. And that he assumes because he says that's consistent with the index that we have computed using certain 5D Yang-Mills approach and so on. So I think it's highly likely that even if these coefficients are not forbidden by symmetry arguments, they will be 1 over suppressed compared to n cubed. Okay, so I assume this and proceed, but this is a bit of loose part of this argument. I think hopefully in the near future, one will be able to argue or show using the input of known supersymmetric partition functions containing circle factor that they are either absent or 1 over n suppressed. But I don't really have a neat argument for that.
So have you seen a similar situation arose in hydrodynamics, where a mixed Chern-Simons term was allowed, not forbidden by time reversal, apparently, and so on. And that term had an unknown coefficient.
Unknown coefficient.
It determined an important parameter in hydrodynamics.
Yeah.
And then Loganai had a beautiful argument relating this to an anomaly in a non-obvious way.
So not just this anomaly.
No, that is a simple argument. Even simple people like us have arguments. But Loga and other collaborators had a beautiful argument relating this to an anomaly in a more complicated way.
I see.
Using some sort of using some sort of Cardi formula.
I see. It's in the setting of 4-dimensional gauge theory?
Yes. I'll send you the reference. I suspect it may.
I see. Thank you very much. Also in the Zohar's paper, I found some confusing comments about his conjecture that he conjectures that these coefficients should be somehow connected to anomalies, and maybe he's referring to that kind of.
He's referring to that.
I see.
He talks about it a lot.
Okay. Okay, thank you. So hopefully, I really want to make a proof of this assumption because, if I don't do this, I know what will happen. Somebody will someday come and they prove that these coefficients are 1 over n suppressed, and they'll claim that they counted large AdS7 black holes. So I want to do it myself as soon as possible. Anyway, with this assumption made, you take the free energy obtained from this Chern-Simons, gauge non-invariant Chern-Simons term, where this omega 1, omega 2, omega 3 dependence is coming from 3 holomorphic derivatives. It's the Cardi behavior of 6-dimensional CFTs. And you make a Legendre transformation of that, very similar to what I explained for AdS 5 times S5, and that accounts for precisely the large supersymmetric black holes in AdS 7 times S4. Again, this function itself has been found before we did this kind of calculation by Zaffaroni and collaborators. They're somehow marvelous. They get this function by, I don't know how they got it, but I think they're also inspired by anomalies, but they wrote this down, they do Legendre transformation, and they show that it accounts for the properties of black holes. So I was quite amazed to find these papers, but eventually I found that it can be derived from Cardi anomaly, this Cardi formula and anomaly and so on. But anyway, this kind of fact that this function explains the properties of known black holes has been known from early this year.
Okay. And this is supposed to be exact. Your formula, your derivation works?
Only for small omega 1 to 3, but for known black holes, they show that it explains the known black holes even away from the large black hole limit, similar to the AdS 5.
Right.
Yeah. So it should be a free energy describing this local saddle point at least. Okay.
They don't get the formula by localization.
No, they just write it down. It's not field theory study. They write it down and they make some comments on supersymmetric Casimir energies, which I really don't understand. But anyway, they just write it down. Yeah. I mean, to be honest, this formula and the analogous 5-dimensional black hole formula was the first, one of the first motivations that I felt convinced that I could derive it. It's anomaly, so it should be easily derivable.
So again, the index gives the right partition function. It's not the bound or something.
Yes, it's saturating on known solutions. If you impose the charge relation by hand, yeah. And again, the important part is that these numerator all-symmetric chemical terms have order 1 imaginary parts. Only then you have macroscopic entropy. Yeah.
Is imposing the charge relations related to choosing particular values of the imaginary parts of the chemical potential?
No. Let's say it this way. So so imposing so distributing the imaginary part, the Cardi limit, omega 2 is small. So it's just distributing 2 pi I to this 3, let's say equal electric charge. There's only one way, distributing them 1/3, 1/3, 1/3. So it's just by symmetry argument, it's quite obvious. Yeah.
So is there a charge relation even in AdS?
Yes, yes. We have an explicit expression by now. Yeah.
It's not the BPS relation.
No, it's an extra condition having to do with the smoothness of smoothness of near horizon, well-behaved nature.
At the same time, that would
Yeah, exactly. It's a bit more complicated, but similar nature.
And there's no field theory understanding of that charge relation. Not in your work, not in Benini's work, not in.
As far as I know, no, I don't understand. Actually, one of the projects I want to do is to see. I mean, in AdS 5 and AdS 7, I got this and I superimposed known charge relation to study known black holes. But even these Cardi friends, if I don't superimpose known charge relation for black holes, I'm doubting whether it has some information of hairy black holes as well. If I don't impose this, I want to basically study this free energy or the AdS 5 free energy in the small black hole limit, I told to you personally, and try to see if that sees a kind of non-interacting mixed picture of small black holes and the hairs. So I don't impose the charge relation. I allow the charges to be violating the charge relation. And I try to understand hairy black holes by superposing the known black hole satisfying charge relation and the hair. So I take certain charges away from black hole so that the black hole is demanded to satisfy the charge relation, but with extra charges which I distribute to gravitons. And I really like to see whether they can be in the thermal equilibrium with each other and so on. I mean, just by using this free energy and so on. So I'm still not sure whether this free energy describes known black holes only or whether it has a room for hairy black holes as well. So, yeah. So to be very conservative. Okay, any other questions so far? This completes my explanations on even dimensional CFTs and odd dimensional AdS. So in the remaining time, I'm not sure how much time remains, but I'll show you two small episodes on odd dimensional CFTs. It's very dirty technical work, but I wanted to deliver some messages about that because I think it's very curious. So yeah, it's getting into very, very small and dirty problem. So I try to investigate with my student, Sunjin Che, the 5-dimensional CFT index for the D4 brane system that I explained to you, engineered by Cyber. So we don't know any Lagrangian description for any observable cannot be computed convincingly. I mean, most observables cannot be computed convincingly if you don't have Lagrangian description. But somehow, inspired by these effective Yang-Mills theory intuitions and using some techniques of supersymmetry, my collaborators in Korea have, I think, I should say that they basically proposed a matrix integral formula, unitary matrix integral formula, which is suggested to give the index of the 5-dimensional CFT on S4 times S1. And it's strongly, the proposal is strongly constrained by effective Yang-Mills theory description, but I think it's logically no way to derive them because we don't have a description. But they anyway wrote down certain suggestions for the formula, which just turns out to work for this and that cases, and it seems to be a consistent formula, at least as far as we understand so far. So anyway, the contour integral formula, inspired by the Yang-Mills gauge theory intuition, was it's a unitary matrix integral. It's similar to alphas that are for maximal super Yang-Mills. The integrand turns out to be much, much more complicated. Integrand turns out to be consisting of a factorized part, where each part is nothing but the so-called Nekrasov's instanton partition function on omega deformed R4 times S1. So sorry, epsilons, what I wrote, epsilons are all omegas. So S4 has 2 rotation parameters, which I call omega 1, omega 2, or epsilon 1, epsilon 2. So this is the quite amazing and very complicated proposal, which just seems to work. So I want to see whether it continues to work in the larger Cardi limit. And if it works and counts black holes, I want to get some lessons from that. Okay? So it's good to get lessons by advocating some nice working formula. But this part is very complicated. So this, what's called the Nekrasov instanton partition function, gets 2 contributions. First of all, it gets contribution from the so-called perturbative part of gauge theory, and it gets some instanton corrections. perturbative part, at least in the Cardi limit, takes very, very similar form to the four-dimensional Yang-Mills theory, mainly because of the fact that S4 and S3 both have two angular momentum. So its Cardi limit of the integrand becomes 1 over omega 1, omega 2 times bunch of trial-log functions that has the same origin as the four-dimensional integrand, with each line coming from vector multiplet of SPN, hypermultiplets in stupid representations, but the rough structure is the same. Instanton corrections have very, very complicated form, and this very, very complicated form plays some roles, very, very certainly, to make this n to the 5 half scalings possible. Okay? So the instanton correction, by that I mean the following. So the 5-dimensional field theory has spatial slice, 4-dimensional spatial slice, and temporal direction. So Yang-Mills instantons, I mean the solitons solving either self-duality or anti-self-duality equation. So they are tunneling effects in semi-classical 4-dimensional Yang-Mills, but they are providing the classical solitons for solitonic quantum particles in 5 dimensions. So these kind of particles form a much, much more complicated bound state spectrum than usual gauge theory. For instance, if you go to the Coulomb phase of this gauge theory, consider the bound state of W bosons and these non-perturbative particles. They form infinite tower of quantum bound states in Coulomb branch, somewhat like hadrons, mesons, or baryons in QCD. So I'm really like to view this kind of instantons as partly confined bound state, meson-like or baryon-like bound states, consisting of some noble partons. But this is all words in the air. I don't really understand what I'm talking, but I think this kind of picture could be true. So instantons and quantum bound state of instantons, I'd like to view as the bound state of novel partons like quarks and gluons in this novel confining phase of high-dimensional quantum field theory. This is a picture that has to be rigorously justified or studied. So anyway, given this setting, we can ask the following. I explained to you that the expression is given by similar unitary matrix integral, where all the eigenvalues are living on the unit circle. Can we take the similar Cardi limit, also taking the larger limit? Can we take the Cardi limit similar to what I did in the four-dimensional Yang-Mills theory? So in the four dimension, I demanded, which is proved by Honda, I think recently, that all the eigenvalues are on top of each other, so that the apparently broken gauge symmetry gets maximally restored. So I told it that maximally deconfining saddle point. Will that work for 5-dimensional theories as well? And that's basically demanding all the phases of these eigenvalues to be equal on the unit circle. Will that saddle point work? The simple finding is that merely with this instanton correction of the partition function, this saddle point doesn't exist. Okay? Because of the very singular behavior of the instanton part of the free energy appearing in the effective integrand, effective action of the integrand. So the instanton part of the partition function is very complicated, and it's one of the reasons it's complicated is that when the gauge holonomies are on top of each other, or Coulomb webs are on top of each other, it exhibits characteristic divergences on top of this Cardi divergence. Its divergence is technically caused by instantons having internal moduli space, which is non-compact. So instanton has this size moduli. Nobody understands what this really means. But people have some wild conjecture that it has to do with the positions of the instanton partons or something. But anyway, due to their presence, if you try to put them all on top of each other in the unit circle, the integrand simply diverges in a really, really bad manner. So you can't really imagine finding such saddle points in a similar manner as 4 dimensions. What this singular behavior does is it's forcing us to complexify these holonomy variables living on the unit circle to a complex plane. And now it becomes a complex cylinder. Eigenvalues are forced to be deviating from unit circle.
But is the divergence good or bad? Why isn't the divergence dominating the partition?
I think the reasons are following. If you just try to so the reason why it has some singular denominator factor is, for instance, the Coulomb phase. If you expand this in this exponential of holonomy, in the Coulomb phase, this is physical fugacity of electric charge. If you expand that, you get infinitely many series, and that's accounting for infinite power of this hadron-like bound states of instantons and W bosons. And if it's really, really being divergent, I think, normally the liberated quarks and gluons have less degrees of freedom than just meson things, right? So if you just stick to the unit circle, I think this bad mesonic behavior is being manifest. while if we are to seek for a deconfined saddle point, the sensible saddle points are really made by complexifying the holonomies and letting it spread along this complex direction. And in a sense, technically, these kinds of divergent behaviors are really pushing the eigenvalues away.
Well, this is what I'm not understanding. I thought divergence, you want log z to be as large as possible, right? That's the best value.
Probably yes. But,
so why is divergence pushing it away rather than pushing it towards? I would have thought the sine squared was up in the numerator, it would be pushing it away.
Yeah. I should carefully investigate the sign in front here to understand. Yeah, and then I mean the complex plane, so I should really investigate carefully.
Yeah, maybe it's
no, but I'm confused. I was always confused with this because I think trying to get a saddle point on this circle, perhaps it might have to do with some ambiguity of this 5-dimensional partition function.
Yeah. One comment that might be useful. You know, if you compute a partition function of pure Chern-Simon's theory.
Yes.
When you compute it on S2 with Wilson lines, when you compute it on S2 times S1, you get a sine square, exactly this kind of factor in the numerator. That's just Harmonic.
Yes.
When you compute it on a genus G surface,
it's 1 minus G.
You get it with a 1 minus G. And so naively,
that's an attraction?
Well, it looks like an attraction, but you know, there's some lore that there is something that you've not done right. And those configurations with, you know, in Chern-Simon's theory, those are discrete values, these alphas.
Yeah.
And configurations with alpha equal are just disallowed.
I see.
The best place to look at it is the paper by Blau and Thompson.
Okay, yeah.
In which it's a beautiful paper, gets everything right except this thing they don't know what to say. So
I see.
And then it was clear that had it existed, it would be an attraction.
I see.
But somehow that's excluded.
I see.
It's, you know, you have great tests because you get fusion rule formulas and so on correct if you just exclude this one.
I see.
I'm not sure it's related.
I see. Yeah.
But even if the coincidence points are not allowed, it is still attractive.
Yeah, in that case, you know, they've got some exact results. They don't need to do saddle point. So you have to take all, including one away, to get the right answers. And those are giving you the maximum concentration. But maybe that whole thing is summarized for him by a saddle point that lies somewhere else.
I see. Yeah, so I think at this stage, some things are empirical.
Yeah.
So anyway, you get very well-behaved saddle points. If most of the eigenvalues are taken away from this unit circle and they have to spread in the real direction. And actually the balanced spreading turns out to be this imaginary part, this along the cylinder, being n square root of n. Okay? And very technically, this is similar to what has been done by Jafferis and Pufu 7 years ago on phi sphere. They start from scalar integrals on real line. They are forced to be spread, I think, by the same effect. But I think the physics underlying it has never been addressed. I mean, they just found such saddle points, which explains the large n free energy agreeing with gravity. And here the spirit is somewhat similar, but as Shiraz mentioned, the detailed roles of this singularity is slightly obscure to me. I think clarifying that might be the best way of getting maximal hints from this kind of exercise. What kind of roles these hadron-like bound states are doing to allow us to see these deconfined degrees of freedom. Okay. So anyway, they are accepting this kind of this spreading in the complex plane. And there's a little bit of more technical magic that happens, which I'll not really try to emphasize more. But once with this spreaded eigenvalues, you can do the calculation of large n and also Cardi behavior of the effective action. And we have done it for various models, this D4 brane model by Seiberg and similar variations. And it all exhibits the following behavior of the free energy. It all behaves I take a large n and Cardi limit all together. I get the characteristic Cardi behavior, and this is cube of the delta, which is the chemical potential for SU2 R symmetry. You have to keep order 1 chemical potential as well. And this part is, this is the gravity notation, but field theory, I always get n to the 5½ with precise computation, precisely computed order 1 part. And depending on all models, if you do the Legendre transformation and get entropy, it agrees with the Beck-Einstein-Hawking entropy of supersymmetric AdS6 black holes, which were found by David Cho. Before doing exercise, I never expected anybody worked on supersymmetric AdS black holes, but there are results in the literature. I was very surprised. But anyway, it precisely agrees with the entropy of known AdS6 black holes. But anyway, since there were many loose steps here, starting from the basic formula for the index, I think the most important thing to be done here is to understand why we got this correct expression with this kind of saddle points and so on. But I think it potentially contains a lot of information on how these enhanced degrees of freedoms are happening. And what the role of instantons are, right? And since this kind of divergence is caused precisely because of the presence of this internal moduli of the instanton, interpreted as the parton's coordinate, I think scrutinizing the physics of this kind of calculation will tell us important about this mysterious higher dimensional field theories. Anyway, this is the, yeah.
So suppose I wanted to understand the saddle point in terms of an eigenvalue density
Yeah.
in the complex plane.
Yeah.
Or in the complex cylinder.
Yeah.
So it's not like the, it's again like the unit circle gets deformed to something else, but it's overall two-dimensional spread.
Yeah.
Is that right?
So
the entire complex plane?
Yeah. Strictly speaking, I do the calculation in the simplified setting because I take omega to be small, and the remaining chemical potential delta is required to take a real part of delta, which is very, very small because of high charge, and the imaginary part is taken to be order 1. So imaginary part is the dominant part, and in this setting, if you get close to pure imaginary value, the saddle point distribution can be just obtained on the real line. You can just consistently show that. But with this deformation, there should be certain deformation, and the problem will be slightly more complicated. But in this asymptotic limit, it's on the real line. Yeah. So it's fun exercise, but the physics is still quite unclear. Good. The last part is M2 brain. I'm talking about too many things. But I'm mentioning this because this is secretly where my whole projects began. I mean, it's something like 2 years ago or something. I was really modest. I was never having in mind this AdS black holes and so on. I was simply a bit uncomfortable about the way people understood N3 from the M2 brain field theories. You know, we have lots of great understandings from three-sphere partition function, which turns out to be the vacuum entanglement entropy and giving, but I wanted to get this number from counting some Hilbert states in the Hilbert space. And as far as I could see, that's never done. So I wanted to just do that modestly. And I wanted to do it with the index, but index turns out to be much more complicated. It's a holonomy integral, but it has an infamous operators called monopole operators. It's a non-perturbative object. It's kind of disorder operators defined by singular boundary conditions of fields, and these monopole charges have to be all sum over to get interesting strong coupling physics. This was very difficult.
Could I ask a quick question about that?
Yes.
Suppose I just look at your beautiful formula for the index.
It's not beautiful anymore. It's the dirtiest.
And you keep only the flux 0 sector. Okay? And then you take the full formula.
Yeah.
Does that make the index larger or smaller?
I think that will just give n square. You know, it's just perturbative gauge. Let's say which gauge. Well, it's just it has n square modes here and there, right?
So it would make it larger, right?
I think so. Yeah, I think so.
Meaning you add the phases and do everything.
I think so. Yeah.
You just take the formula with flux 0 sector.
Yeah.
You get n square. But if you take the formula with all fluxes, you get n to the 3 halves.
Yes. Yeah. I think this reduction of degrees of freedom, that mechanism is the key here.
Yeah. So the monopoles are key to reducing the degrees of freedom, right?
Yes.
But configurations
yeah.
in Euclidean path.
Yeah, but I wanted to get a more better picture. I mean, saying that degrees of freedom are reduced is, you can say that, but it's more abstract. I wanted to see where that degrees of freedom comes from.
I understand, but I just want to understand technically first.
Yeah.
That at the technical level, it's the sum over fluxes that is reducing the degrees of freedom.
I think so.
This is clear.
I think so. Yeah. But anyway, what I wanted to do is the following. I'll explain the detailed problem in the next slide, but my problem was very modest. So since the conformal field theory partition function, or indices are somewhat messy and complicated, I wanted to study the partition function of indices of solitons, like vortex solitons in the Higgs phase, in a model that Higgs phase exists. And I'm counting the spectrum of massive particles, but I wanted to take the Higgs vacuum, or Fi prime, to be small, make the vortex light, and try to see whether I see some n to the 3½ degrees of freedom emerging when the vortices are becoming light. Vortices are basically similar to monopole operators, and the exercise started from there. And suddenly from the vortex partition functions, if you tune the vortex fugacities and so on, I suddenly see n to the 3½. And then I realized that these vortex partition functions in a new formulation of the index is a building block of this index on S2 times S1. You roughly cut the two spheres into north and south hemisphere. You glue this two vortex partition function and suitably sum over various Higgs branch points. There are formulas in various theories that gives the index in an alternative form. So once I got vortex partition function n to the 3½, I wanted to use it to understand AdS for black holes. But this turned out to be the most difficult question among all the AdS CFT examples I explained to you. So this is the last project we are struggling with. But anyway, my motivation was started from here.
These vortices play, the instanton particles in the 5D play a very similar role to the vortices.
Yes, yes, but yes.
So those would be crucial there.
That's hidden. That's all hidden in the technical magic that I didn't explain to you. Shall I talk about that? So I think instanton particles are playing certain important roles in making this saddle point important. But if all these parts are included, how would you be able to compute things at all? So the technical point, which was first observed by these people, is that once the eigenvalues are spread with width being n to the 1½ on the real line, you're basically going into the Coulomb branch, giving large VF to the scalar. If you go deeply into the Coulomb branch, these instanton partition functions are highly suppressed, because if you're in the Coulomb branch, the one-loop inverse gauge coupling gets linearly corrected by it's kind of asymptotic free theory. So once you deeply go into the Coulomb branch, you can basically use the Coulomb branch effective action, and that simplifies the story. So although instantons are playing certain roles in making these saddle points important, at the technical level of calculation, only the perturbative part is necessary. Here for the vortices, I think vortices are playing much more important role than that, okay, for reducing these degrees of freedom. Anyway, the point was that, what I'd like to deliver was that unlike higher dimensional theories where we have no microscopic QFT description, by now in 3 dimensions for M2 branes, we have way too many field theory descriptions. We have the famous ABJM theory given by Chern-Simons matter theory. We also, but somehow it turns out to be not the ideal setting I wanted to study, because I was basically trying to avoid using this formula and use the vortex partition function instead. But I think the spectrum of vortices are way complicated in Chern-Simons method than Yang-Mills method theory. So in principle, it can be done, but I don't know how to do. So I deliberately try to avoid ABJM description, trying hard for several months and then giving up. Alternative description that you can see for is just a Yang-Mills method-like theory. One obvious candidate is a maximal super Yang-Mills living on D2 branes. We know that in principle they should be flowing to M2 brane theory. But somehow for technical reason again, this maximal super Yang-Mills theory has been a notoriously difficult setting to compute quantities invariant under the algae flow and also free of certain infrared divergence problems. So somehow technically this is very difficult. I don't think anybody has used this setting to really study the supersymmetric partition function in the recent 10 years. I mean, yes, that's so there's a trick that has been used by many people. I'm not sure whom, but in recent 10 years, Kapustin and company has extensively used that, and other people. The simple idea is to not just consider a stack of D2 branes, but add one D6 brane. Okay? So in the UV, it preserves half the amount of supersymmetry. It has one more fundamental hypermultiplet from D2 and D6. But in the infrared, using string theory arguments, you can expect this to flow to the same M2 brane theory, because the low energy limit in 3D is a strong coupling limit. And if you take the strong coupling limit of 2A theory, D6 brane is nothing but the Taubner space with single center. It just geometrizes to nothing, just flat space. So we have a string theory belief that this should be flowing to the same superconformal fixed point of M2 brane system. And the nice thing is that it's just Yang-Mills matter theory. It has one fundamental hypermultiplet, so it has Higgs branch. And I can study vortices there, and I can make the factorization formula of this index in a much more simpler way than the other models, I think.
Just to mention, this theory came up in the last data infosys lectures, which was last week by Silvio.
Ah, he talked about this? Yeah, Nicole. He talked about precisely this model? What did he do? Yeah. Okay, I'll ask you later. Okay. Yeah, I know he has been doing interesting things with this, but yeah, I'll ask later. Good. So the point is to study the vortex partition function, use it to compute the Lagrange Cardi limit of this free energy and try to compare with AdS for black holes, and it works. So I don't know how important this stuff will be, but the Higgs branch is turned on by basically turning Higgs branch. We study Higgs branch and vortices, and vortex solitonics is basically after you turn on certain Fi parameters, isolating the Higgs branch with other branches. And the Higgs branch equation for the fundamental hypermultiplet and a joint hypermultiplet is basically a very well-known equation. It's called the AD-atom equation for instantons because we are dealing with D6, D2 systems. So it's an instanton equation for U1 gauge group. And it's a typical Higgs branch point for a joint and fundamental scalar. A typical point can be taken this way. You just give some vortices, phases of these non-zero scalar values at infinity to form various kinds of vortices. So this, I think, is a kind of novel vortices, which still are in certain literatures. And you consider the partition function of, or index of this vortex, giving some fugacity, making the temporal circle compactified. Also introducing some angular momentum parameter for spatial rotation. It's called omega background. It's playing our role of small omega in the Cardi limit. So you compute this partition function, giving some asymptotic Higgs VAV. Okay? So it's an R2 times S1 index, which can be defined in suitable ways with 4 chemical potentials. But this formula is a bit difficult. I mean, one way of presenting this formula is to make a series expansion in terms of vortex numbers. And that's an infinite series. With that series, you don't know how to do Cardi or Lagrange approximation. A very nice way of reformulating this Higgs branch partition function has been proposed, has been known from time ago by reformulating it as a disk times S1 partition function. It's a hemisphere, if you want. And this partition function is known to be related to the Higgs branch partition function of vortices once you give a suitable Neumann or Dirichlet boundary condition for the fields, so that you give Neumann boundary condition for the fields that you want to give VAV. Okay? So once you make this kind of formulation of the vortex partition function, the disk times S1 partition function, like many other compact partition function, space partition function, compact space supersymmetric partition function, admits a simple holonomy integral. So S is nothing but exponential of I alpha that I kept using. And it's just holonomy integral. There's no sum of vortex numbers, like no sum of monopole charges, so on. And this has been derived by Yoshida and Sugiyama. And the fact that it has no vortex sum explicitly is the key point in which we can make a Cardi and Lagrange analysis. The vortex sum comes out in a subtle manner. I mean, these are what's called the infinite Pochhammer symbol or quantum dilogarithm. It's a simple function. If you try to evaluate this integral one by one by doing a Resid sum, part of this Resid sum gives the vortex sum, okay? Vortex number sum, so like the monopole operator sum. But in this contour integral formula, no sum, sum is all made in a sense, okay? Hidden in this pole structures and so on. So I think it's just unit circle. I mean, in their paper, they never specified the contour. But in this deep inside the Higgs phase, we just did the unit circle integral and got the expected vortex partition function in many models. So I think it's just unit circle.
So in that factorization formula, you have Z vortex with the label P.
Label
Yeah.
P. P. Yeah. So I implicitly specified which point in the Higgs branch I am. I mean, if you change the Higgs branch point you want to be in, you have to give hopefully more complicated boundary condition and do the calculation again, and then the integrand will change. Okay? Integrand will change because if you give scalars Neumann boundary condition, it appears in the denominator. If you give Dirichlet boundary condition for scalars, only fermions come and it becomes numerator. So it affects. I mean, I haven't seen any results on contour, but empirically, to the unit circle integral in all models I studied, it just works. In their work, they try to avoid mentioning contours, but I think it's a unit circle, at least empirically. I have no clear logical understanding. But anyway, I'm going to do the Lagrange Cardi saddle point calculation, so hopefully that issue may not be that important. So I did the calculation of the Cardi limit corresponds to taking this beta, what corresponds to omega. So it's two-dimensional space. You have only one omega. So taking beta to be 0 is taking small q to be 1. So I approximated this free energy, this integrand as to exponential of something, and do the large n and Cardi calculation, very similar to what I did for 5-dimensional CFTs. And once you get that, we can employ the factorization formula for the superconformal index in terms of the perturbative part, vortex on the north pole, and the anti-vortex on the south pole partition function. And you have to sum over various Higgs branch points. Okay? So you can, in principle, compute this partition function using alternative methods, and you can evaluate each term, Cardi-like behavior and large n behavior. The point is that we haven't searched through all possible Higgs points participating in this formula. Possible Higgs points participating in this formula, again labeled by Young diagram, is complicated. We've only did it for one specific Higgs branch point. We have no derivation whether it's the most dominant one. We've only shown that for subset of Higgs branch points, the point we have studied is a dominant one, which means that giving the Neumann boundary condition for the half of the hypermultiplet, Dirichlet boundary condition for the half of the hypermultiplet. This is the kind of simplest kind of boundary conditions one can give. And corresponding to that Higgs point, we evaluate the free energy. And to get the superconformal index, assuming the dominance of this saddle point, you just get twice of the two vortex partition function, which is this. Okay? So T1, 2, 3, 4 is the SO8 R-symmetric chemical potential. Beta is omega, small Cardi parameter. And this is again constrained this way for the expression to be the index. Again, you Legendre transform it and compare to the known AdS 4 times S7 black holes imposing charge relation. This explains it. So it became so easy now, at least to get the numbers and entropies right. Yeah. And this has been the project that started my program, but it's solved at the last moment. I mean, there were last moment technical difficulties which plagued me even at the time I was coming here. Early this week, my students solved this problem completely, and I think we have a full derivation of this free energy, assuming that the Higgs branch point we have chosen is the dominant one. Okay, so there are some assumptions, but I think it's quite reasonable to make such assumptions. Yeah, because assuming the dominance of that saddle point, at least we explained large black holes. So yeah.
So this should be AdS 4 times
CP. You're referring to the ABGM. ABGM at large Chern-Simons level is due to 2A on AdS 4 times CP3. But I'm studying ABGM at level 1, so it's M theory on S7.
But this calculation we did for D2 brains.
D2 brain, but it's supposed to flow to the same M2 brain theory. Yeah. So in this kind of approach, I only have access to S7 without any orbifold. Okay. So only at level 1. Yeah. So that's all I want to say. The conclusion of today's lecture is that for even-dimensional CFTs, we have a more abstract control over the Cardi limit of the free energy from 't-Hooft anomaly and so on. It rederives sort of the maximal super Yang-Mills free energy, and it strongly constrained the Cardi free energy of 62.0 CFTs. I'd like to claim that I almost derives it, but I'll try to be modest. There are some gaps to be filled in. That explains large supersymmetric AdS7 black holes. And for odd dimensional CFTs, you just have to do some dirty studies. It might be good if you have some abstract methods like this applicable to here, but it might be interesting to develop such things. But so far, I have shown to you the result of certain dirty calculations. So this is the last lecture. So briefly summarize with what I think could be some immediate interesting directions. The Cardi free energy has more general usefulness beyond explaining black holes in the larger limit. So at central charges fixed, A and C central charges, it might be interesting to study the implications of the Cardi free energy of 4D n equal 1 SCFTs. Okay? For instance, trying to see when they develop macroscopic entropies when charges are large and so on. I think there will be some interesting things to do. And it will be interesting to develop more unifying features of all even-dimensional CFTs in the Cardi limit. Because in 2D limit, it has been used so powerfully, we may try to get a more unified understanding on this even-dimensional CFTs behavior. It will be more interesting to understand the physics of hairy black holes from the 4D index. I just shown a few evidences claiming that they should exist, but their physical properties are not very much explored. As I explained to you in the middle of the talk, I'm not still sure whether this Cardi free energy describes this kind of free energy in the Cardi limit or beyond, describes non-hairy black holes only, or whether it has some information on hairy black holes as well. So I'd like to study this question in the very near future. And probably it'll be good to have some more control of the analytic properties of these hairy black hole solutions. Okay. In the higher dimensional CFTs, I think the calculation I've explained to you will be shedding certain useful information about the novelty confinement in the CFT. So it's a challenging question, but I think it's worth thinking about it further because we have concrete calculation which actually works. Finally, in four-dimensional black holes, we've counted the entropies of large and AdS black holes using this kind of Cardi formula. But it will be really interesting, at least in the weakly coupled picture, what kinds of operators make these black holes microstates. And I've thought about this question with Shiraz, and many other people thought about it. But I think this is wildly open question still at the moment. Okay, so I'll finish here. Thank you.
Any questions at HRI?
Are there?
In the 3D index, there is this limit that one can take, the Higgs branch and Coulomb branch limit, in which only Higgs branch operators contribute and Coulomb branch operators contribute respectively. The Higgs branch limit has a technical feature of just being an integral, while the Coulomb branch limit has this sum over monopole sectors.
I see.
So I was wondering if in this specific limit, whether
Its limit is just something like low temperature limit projecting out certain states?
no, it's a particular, it's like a
Tuning.
It's like a micromark.
So it's a kind of Pater lower temperature limit. Oh, I see.
It counts higher supersymmetric states.
I see. I vaguely remember that I've so far never paid attention to that, but I should try to do that. Yeah.
Because if they also contribute to these black hole states, so who had an algebra of these states also.
I see.
And I wonder whether the algebra of those states.
I see. That exists for n equal 4 theories. So you,
n equals 4 theories.
I see. Yeah. I'd like to start. Since you say it's similar to McDonald's sector, probably there'll be a room for predicting more exotic black holes and so on. Yeah, thank you.
It also means that normal black holes don't exist.
It will be interesting to test that. I mean,
also because
yeah.
So at the technical level, you said the cut down the degrees of freedom is coming because of the sum over monopole sectors. Right?
Yeah.
So if you look at Higgs and Coulomb, this would say that Coulomb branch more likely have this, but there is mirror symmetry in which this Coulomb branch is like a Higgs branch of another theory.
Yes.
And that will be given just by an integral now.
I see.
Then it's perhaps
I see.
I think it suggests that that this does not have the large group.
Thank
Because
you.
it would be really a bummer.
Yeah, sure.
Like n square or something.
Yeah.
No, I think it suggests that the coefficient of n square is 0 in this end.
Anyway, I'll have
Otherwise it would be a
yeah.
shock, right?
Sure.
Because you'd have n squared, one calculation gives n squared. But we know that nothing is n squared.
Yeah. Anyway, I want to take a look at that. Thank you. Yes. Yeah.
Question. I had a big question, so tell me a specific question. My big question is this. Suppose I'm in n equals 4 animals.
Yeah.
And if you don't mind, I draw a graph for my question because it will become clear.
Yeah.
What I want to do is to understand how the number of supersymmetric states scales with energy. Okay, so suppose we have S of supersymmetric states as a function of energy.
Yeah.
Okay, so we know two ends. The first end we know is that here we have some power law. I'm going to write 5 by 6.
Yeah.
Roughly. Sorry. Yeah, right.
Yes.
The other way. E to the power 5 by 6.
Yeah.
5 by 6.
Yeah.
And here where E starts off at order n squared.
Yeah.
We know that the entropy is n squared times some function, I don't care what at the moment,
Yeah.
of G by n squared. Right? Now, I want to say, how can these two match to each other? If I just put E is equal to n squared here, I get too few states. Because if I just put n squared, this scales like n squared to the power 5 by 6.
Yeah.
Whereas here, it should scale like n squared.
Yeah. Yeah.
So there has to be a period of acceleration somewhere in between here and here.
I see. I see. Yeah. Yeah.
Okay? So it can't just be that the answer is just the gravitons
Yeah.
and the black holes. There has to be something interesting happening in the middle.
Mm.
Okay. In the non-supersymmetric situation, that interesting thing was Hagedorn behavior.
Mm. Mm.
That's what allowed this to match to that.
Mm.
Because there was this acceleration, exponential
Yes.
acceleration.
Yes. Yes. Yes.
Okay. Now, in the supersymmetric thing, something has to happen. It has to have new. It seems to me that it's likely to have new physics that's neither gas gravitons nor black holes.
Yeah.
And I was wondering if there was any way to access that.
Yeah. I think that's. You mean the Hagedorn meaning the weakly coupled analysis of partition function?
Yeah, in the weakly coupled analysis, but we also know it's strong coupling
It's also Hagedorn?
because of string theory.
But Hagedorn temperature is just growing with tension of string, right?
Correct. But that growth is lambda to the something, which is much smaller than n squared. So even when lambda is relatively large, let's say a million,
I see.
n is like a billion. So
Still you think Hagedorn should be?
yes, it's just the fact that in string theory, in weakly coupled string theory, there is a Hagedorn regime,
Sure. Yes.
which is then cured by black holes.
Yes.
But the Hagedorn is what allows you to interpolate between the relatively slow growth of gravitons and the large number of states of a black hole. Now, here it seems unlikely there's Hagedorn behavior
Oh yeah.
because we don't have a Hagedorn spectrum of BPS strings.
Yes. Doesn't see lambda.
Yeah. So there's something else. It seems like there's something else interesting that's playing the role of the Hagedorn behavior. And I was wondering what it might be, and whether it seems like a technical question that we can address from the index.
I see.
Because you've told us that the index grows like some power, maybe not 5 by 6, but some power.
Yeah.
You've told us that the index has this.
Yeah.
So somewhere in the middle, it has to have the intermediate stuff, and I'd love to be able to pull that out.
I see.
For the non-supersymmetric weakly coupled matrix model, you were able to see this.
See everything.
I see.
It seems to me that you might think that it might be like giant gravitons, like Abhijit was suggesting at some point, and maybe it is. Maybe the first interesting question is of what energy does this get cut off, and what energy does that?
Long ago, you had an explanation of small AdS black holes using giant gravitons.
Yes.
Would that be relevant? You think?
Could be it's like n.
Yeah.
Could be that between n and n squared, that's an interesting function.
Yeah.
And it would be really great that to predict that from Jackson, or from some other physics.
Yeah. I see.
So the first thing to do would be to pull it out.
If it's n is where this is failing.
This fails at x. But and of course, it's possible that there's some other scale somewhere. Something else happens at n.
Right. But the first scale should be n.
I guess. The first scale should be n. Naively, that n cuts down the radius.
Matrix relation.
Yes. So it does. What we need is a speeding up. So that naive thing doesn't sound by itself enough. It's you were asking where are the new states of the black hole in Engel's theory. It seems to me that new states have to show up even before you reach black holes. And that might be an easier thing to answer.
So some intermediate scale of n.
Yes.
Between 0 and 2.
Yeah. But the first question, this is a very abstract question, of course, a big question, but there's a technical question, which if one could just better control the larger limit of the index, one should be able to answer. Which is just use the index to pull out this function. And then later we try to figure out what it is, what it means.
The modulus, right? Modulus count.
Yeah, the modulus counting, exactly.
I see.
To use it to pull it out, not just. Now, it's very likely that will never dominate the. It's very likely that will never dominate, the region in between will never dominate the thermal answer, the canonical answer. Simply because you probably need an acceleration at a power faster than 1, which is negative specific heat, which never dominates us. Okay? But usually those things show up as unstable satellites.
Yeah. I see.
It seems to me to be an interesting question and one that potentially could throw light on new physics.
I see. I see. Thank you.
But even without, even with counting states with sign, this gas graviton fails at an already, right? So
Yes, something
even
takes
if
over.
you don't, if you just count even with signs,
Yes.
then also something changes there.
Yes. Yeah.
Maybe then that's the cut down when you count it with signs and it's not a cut. No, but
It's a cut down even without signs.
yeah.
So we need some new physics, not just a cut down. I mean, I think from the point of view of Gangler's theory, this cut down is coming from essentially eigenvalue physics. The new states have to involve non-diagonal matrices.
Yes. Yeah.
Because that's how you're going to go to N square.
Yes.
Right. So somehow that new physics you need to start seeing. But I do think that I'm saying this as motivation for better understanding the larger limit of this, perhaps for solving the matrix model. I think if you can solve the matrix model in logarithm, I think that's a very important question. Not just for satisfaction, but also because you might learn new things.
More questions? No? Let's thank you.
Thank you.